Hi everyone, I'm bongjung, first year PhD student in statistical science. Yeah, I'm going to give a presentation about log-concave sampling. So in this presentation, I will review the paper by Dui Bedi, the paper named "The Log-Concave Sampling Metropolis Testings Are Best." This paper established the results for time-missing bounds for metropolis testings algorithms for log-concave sampling, and we introduced the main results in this paper. This is the outline of this paper. And so basically to introduce the background for this paper, in this the paper is concerned with drawing samples from a known distribution. But basically this problem is a core computational challenge common to many disciplines with applications in statistics and other many areas involving stochastical models. Because even if the distribution, the target density is available, it is often the case that the the target density is very intractable, so that the sampling is not easy, which is often the case with Bayesian literature where the computations of posterior are very intractable in most cases. In recent years, Monte Carlo chain, Markov chain Monte Carlo MCMC has shown a great success. Most of methods based on SCMC consist of two steps. The first step is to construct a Markov chain whose stationary distribution is either equal to the target distribution or close it to it close enough to in some matrix. And given this chain, the second step is to draw samples from simulating the chain for a certain number of steps. Commonly used MCMC algorithms include metropolis random walk simply MRW, an unadjusted random algorithm ULA or EULA, and matrix adjusted random algorithm MALA. And note that we are interested in these three algorithms. So basically, in this paper, we restrict our sampling problem to low-concave sampling, which means that the target density is proportional to exponential minus fx, where f is convex. And basically, recent works have contributed to provide non-study bounds on this time-missing bounds for non-distributed distributions for sampling from a low-concave sampling, such as Dalian and Chang and Bartlett for EULA. But however, although EULA obtains non-static bounds, the results are hard to quantify, and furthermore, with the fifth step size in sampling, the algorithms may not converge to the stationary distribution if run for a large number of steps. Contrast to EULA, MALA algorithm ensures that the resulting random walk has the stationary distribution because due to the metropolis testings correction step. And basically, non-static missing time for MALA also have been have been derived by both Lave and Harrier and Avale. However, basically their timebars are non-split, so they have limit in extracting a explicit dependency in terms of dimension D and error tolerance delta. So to overcome this limit of non-unstatic time missing bounds for MALA, this paper provides explicit non-static missing time bounds of MALA and extend the result to MRW, but thereby showing that MALA converges significantly better than EULA, at least in terms of the best known upper bounds on their respective missing times. In particular, if the density is strongly low concave and smooth, the delta missing time for MALA scales as kappa d log 1 over delta, which is significantly faster than EULA's convergence rate of order kappa squared d over delta squared. Also, we show that the paper shows that MRW misses all big O kappa slower than compared to MALA. Furthermore, if the density is weakly concave, modified MALA converges in the time scaling as d squared over delta 1.5 in comparison to the d squared d to the power of 3 over delta to the power of 4 missing time for EULA. And in this presentation, we adopt the following notations for the big O and total variational distance and common library divergence, also the target density and corresponding density as follows. Also, we introduced some preliminaries for sampling using Markov chain. So suppose we have an initial density pi 0, then any such Markov chain is simulated in two steps. The first is cross-product step, which we make use of proposal function where px dot is a density function for each x in Rd. And so basically x is the current state, and we sample jet from this conditional distribution as a proposal, and in the accept reject step, the algorithm accepts jet with probability alpha x jet expressed as following, and rejects with or minus alpha. We just said that we can define a operator TP on the space of probability distributions. Given the distribution mu k of the chain at time k, the distribution at time k plus 1 is given as TP mu k. But with respect to mu k, and iteratively, we can express this operator as TP to the power k or to the power of k mu 0. And also, we define the missing time for error tolerance parameter delta as following. So delta is basically the upper bound for the total variation distance between the operator at the time k and the stationary distribution, and this missing time is basically the minimum number of iterations to achieve this bound. So we also reviewed some algorithms interested in this paper. So MW is basically in MW, if the current state is Sk and the proposal is just a standard Gaussian, then the proposal is given as following with the step size h and the evolution k plus 1, which is sampled from standard Gaussian. Since the standard Gaussian is symmetric, the acceptance probability can be expressed only based on only pi, and we accept use proposal uh, with this with following probability and reject otherwise. So basically, because MRW does not use the gradient of f, it's basically just older sampling algorithm, and basically it is also known that if um, uh, they're known that if the they're known that the chain has a positive density of jumping node from any state S to Y, and hence it's strongly pi irreducible and aperiodic. Also, the chain has a unique stationary distribution. Compared to this algorithm, longevity algorithms such as EULA and MALA are based on longevity fusion. Longevity fusion is basically a stochastic process whose evolution is characterized by following SDE, where WT is a standard Brownian motion on RD. So the natural way to simulate this SD is to consider Ford-Euler discretization with evolution from the standard Gaussian with step size h, which is so this sampling scheme is referred to as EULA. So, but however, this sampling scheme has a problem in the sense that when one uses a fixed step size for EULA, our important issue is that the resulting random walks are aesthetically biased due to the lack of metropolis testing correction step. So it is possible that the corrections may not converge to stationary distribution if run for a large number of steps. Furthermore, if the step size is not chosen carefully, then the chains may become transient. Also, even when the SD is well behaved, the iterate defined by this discretization have missed behavior in the sense that for sufficiently large A's, the iterates may converge to a stationary distribution that is no longer equal to the target density, the target distribution pi. Unlike EULA, MALA, to handle the discretization error, the alternative it considers the alternative way by considering the modified proposal with the metropolis testing accept reject step. And in this, so we also introduced some problem setup in this considering this paper. So basically, we assume the target density to be log-concave, and we assume that minus log pi, where f is less smooth and strongly convex, and we also define the condition number of f or corresponding target density pi by kappa L over m. So now we introduce the main results. So if we denote to the initial distribution mu0, we say mu0 is meta norm with respect to pi if the mu0 over pi over all measurable set is uniformly bounded by beta. And we also introduce functions RNS where R is used for to establish the time missing bound, and W is concerned with the step size. So, and also we denote uh, the operation on the chain or at the case time by for Mala as following in the theorem. And so with any so we any beta were in this initial distribution mu0 and any error tolerance delta, then the Mala has the following um, time missing bound with step size depending on the function W. So uh, so to discuss the result, so if Rs is smaller than or equal to 4, which is possible when S is larger than or equal to exponential minus d, then the the term R, the term that depending on R in the time missing bound can be treated as a constant because it can be made is extremely small. And under this condition, if kappa is small OD, then the missing time of Mala scales as O big O d kappa log 1 over delta. This result implies that the dependence on the tolerance delta is exponentially better than um, big O d kappa squared log squared 1 over delta squared missing time of Euler by Dalian. And also, similarly, we can establish the time missing bound for M of W with a modified step size as the following. Again, so we clearly see that the time missing bound for M of W contains R delta over 2 beta. So again, if under some conditions, we can treat this term as a constant, and then the missing time of M of W scales as the upper scale the log 1 over delta, which has exponential factor in delta better than Euler by Dalian. And if we compare the results between the time missing bound for Mala and MRW, basically we see that um, uh, the missing time missing bound for MOW has an extra factor of big O kappa. Um, so basically, because why such a vector is conceivable given that Mala's property distribution uses the first order information about the target distribution and MRW uses only the function values. It may be interesting to suspect that under some certain conditions, this the sampling classes for Mala and MRW may be separated by this strictly separated by this time missing bound. Now we extend the results. These main results can be extended to many cases. So basically, in deriving time missing bounds for Mala and MRW, we consider the feasible warrant start, but basically it may be not available in practical implementation. But let's consider feasible starting distribution instead. So suppose the gradient is available of f is available so that we can find the unique mode of target distribution x star, and we consider the alternative initial distribution mu star. Then with kappa L over M, then we still have the modified we still have that mu star satisfies the uh, one start with the modified parameter beta as a beta squared. Again, with some step size depending on W, then we have that the both Mala and RW achieves some missing time bound for as following. And to discuss the result, uh, yeah. So to discuss the result, we have slightly modified the time missing bound compared to theorem for theorem 1 and 2, and we and now we can further extend this result. So basically, if we suppose the access to x star is impossible but gradient is still available, and so we can find the S tilde that is uniform that has a is that is epsilon approximation of S star using the gradient based algorithm and have estimated for L by L tilde. Then again, if we consider the following starting distribution mu tilde, then mu tilde, then mu tilde still satisfies the one start with beta tilde. Then with modify the step size depending on W with the algorithm still the time missing bound for mala still satisfies the following time missing bound. It is good to note that when epsilon tends to 0, so that S tilde get closer to S tilde and L tilde also tends to L, then we have the same time missing bound for the in the previous result, which is quite natural result because because yeah, S tilde tends to start when epsilon gets closer to 0. Also, we further extended this result for the case when f is L smooth but not strongly concave, and it is possible that the Hessian is zero matrix. And if we approximate this target distribution by pi tilde, then and also correspond and with a modified f as an f tilde with tunnel parameter lambda, and we also consider the modified w for step size as following, and then we may apply mala to pi tilde not pi, so we consider the modified mala. We further assume that the first moment is bounded by d squared and nu squared and set lambda as following. Then with the modified mala we just mentioned and assume the mean the condition for pi tilde above. Then also for any data were mu0, then we still distribute mu0. We have that the modified monomer still satisfies the following time missing bound. So to discuss this result, did we see that for recurring low-concave densities, modified mala misses in big O d squared over delta 1.5, which improves upon the big O d to the power of 3 over delta to the power of 4 missing time for a Euler scheme on pi tilde by Dalian. So, and also note that we can also similarly derive the time missing bound of big O d to the power of 3 over delta squared for m of w, but yeah, still which has a for missing bound for compared to mala. And to verify these main results, we conduct some numerical experiments. So we consider the density to be Gaussian with a mean 0, and which is clearly log-concave. And with this function, this corresponding f, then we see that f is L smooth with 1 over lambda mean 1 over the minimum eigenvalue of sigma, and M strongly convex as with 1 parameter m 1 over the maximum eigenvalue of sigma, where sigma is the covariance matrix of this Gaussian distribution. And for step size, we consider the following step size for Euler, mala, and MRW respectively. So basically, in this simulation study, the error in quantiles along different directions is used for convergence diagnostics. And using the exact quantile information for each direction for Gaussians, we measure the error in 75% quantile of the sample distribution and the distribution in the least favorable direction, which means along the eigenvector of delta sigma corresponding to the eigenvalue, the maximum eigenvalue of sigma. Then we have the approximate missing time as defined as the smallest iteration when this error falls below delta. So in first simulation study, we conduct numerical experiments for strongly low concave density. So we consider sigma as a diagonal matrix with the maximum eigenvalue as 4 and the minimum eigenvalue as 1, so that the condition number is 4. And fixing dimension D, we simulate the 10 independent runs for of the three chains each with each 10,000 samples to determine the approximation time. And for step size EULA, for to see the time missing bound depending on dimension, we choose delta to be 0.2. And so the following figure shows the scaling of the approximate missing time for strongly log-concave density. And so the figure A shows how the missing time depends on dimension fixing delta as delta 0.2, and the figure B shows error tolerance dependency on 1 over delta. And note that this plot was basically um, calculated as following. So the binary approximate missing time for each walk was calculated as the average of those over 10 replications. And basically, the y-axis are based on the log scale. And we clearly see that, and I also note that the curves are obtained by regress missing time on its d and 1 over delta. So basically, we see that from figure A, we see that the computations reveal that the dimension dependency of Mala, U, and MRW all close to order of D, while the figure B shows the dependency of approximate missing time on the inverse error, 1 over delta in log scale. So basically, EULA uh, uh, has the linear regression of the approximate missing time for EULA has a slope 2.23, which means that the error dependency of 1 over delta squared for EULA. And similarly for Mala and MRW shows that the slope is 0.33, so which is significantly better than the EULA. Now we consider the scenario for weakly concave density with a large minimum maximum arguable of lambda and small minimum arguable of lambda at sigma, then we have that the condition then at the convex parameter m is almost 0. So if we which is almost mimics the weakly low concave density. Again, we consider the same sampling scheme except for the modify the initial distribution, and we consider the step size kappa in the previous slide as by choosing m to be delta over dl for dimension depending experiment. Again, so compared to previous result, we see that for the time missing bound for in terms of dimension dependency, Bala, EULA, and MRW shows that d squared dependence on missing time for d to the power of 3 order for EULA and MRW, while d squared for Mala. But on the other hand, if we fix the dimension, then the EULA shows error, the approximate missing time based on the inverse error of order 1 over approximately 1 over delta to the power of 4, while MRW shows the order 1 over delta to the power of 1.5. So this scaling is particularly verifies the rate derived in corollary 3, and so we demonstrate the gains of model of ULA for the weakly low concave densities. Lastly, we investigate the the relationship between step size and ascendance rate. So if we consider the step size d to the minus gamma with some variety values of gamma for Mala and MRW, note that the step size is chosen so that the ascendance probability does not degenerate for both mala and MRW. Well, to discuss the results, we see that uh, yeah, we see that um, uh, we see that the bounds for mala from theorem one may be not too tight, while that MRW from the bounds from theorem two are very likely to be tight based on the simulation result. So deriving a better time for mala or establishing that the current dependency for MRW is tight, which is tight. So to wrap up, we see that we see that the paper provides non-uncertainty bounds on the missing time of mala and MRW for log-concave distributions, and both mala and MRW shows better missing time than EULA in image representings. And well, all of these results in this paper are upper bounds of missing time, and the simulation results suggest that they are tight for the choice of test sites using the theorem statement. So, um, which we which further motivate the um, further research directions. And also, we saw that the there is a gap between the missing time of first order sampling methods, Marmala and EULA, and then of zeroth order sampling method MRW. And we may interested in delineating this fundamental gap. And also we saw that there is a gap between Mala and MRW, and so we are maybe also interested in if this difference in time scaling is makes the class of methods for Mala and MRW is separated strictly. And these are inferences. And so today I gave a presentation about log concave sampling. Thank you so much.